Ryan's going to be giving the next talk, and Ryan's from the University of New South Wales. So take it away.
Awesome. Thank you, Kane, and thanks to the organizers for putting this together. My name's Ryan Seelig. I'm a PhD student at UNSW, and I'm supervised by Dr. Arnaud Brothier. And today I'm going to tell you a little bit about a new Thompson-like group construction called forest-skein groups that were invented by my supervisor, and we're going to discuss their simplicity properties. So we'll just talk about some motivation for why we want to do this, and I'll take you through the background of the forest-skein formalism, and then we'll talk about their simplicity properties. So I'm sure most of you know, but just recall that a group is simple if it admits no other quotient groups than G and the trivial group. So equivalently, it's got no non-trivial normal subgroups. So we care about these because they are the building blocks of group theory, and if we have a good understanding of the simple groups, then we have, in some sense, a good understanding of what's going on in group theory. So we're focusing on finitely presented infinite groups. So just contrast to, say, finite groups, for instance, we don't have a very good understanding of the simple groups in the finitely presented world. Contrast to the finite world where we have a full classification theorem. So how do we do this? We need to look for examples. And as it stands, there aren't too many classes of finitely presented simple groups out there. If we have a look at the world of all these finitely presented infinite simple groups, there's some groups constructed by Bourget and Moses. There are sort of Cax-Moody groups, and then there are the Thompson groups. And to try and generate more examples of such simple groups, we're going to kind of look in the neighborhood, quote unquote, neighborhood of the Thompson groups. So I'll just recall for you what Thompson's groups are. They are these groups of piecewise linear bijections of the interval. They're defined as follows. What you do, you take your unit interval and you form partitions just by cutting in half. So we can see an element of F. What you do is you take the domain interval, you cut it in half, and then you cut the right subinterval in half again. And you also cut the codomain interval the same number of times. You split it in half, and now we split the left subinterval in half again. And then we basically join the dots. And this gives us one of our valid elements of F. There are two other groups, T and V. And T, you allow for cyclic permutations of your sort of intervals in your partitions. And V, you allow for arbitrary permutations. Now, these restrictions on the type of bijections we do on the unit interval just by successfully cutting these intervals in half allow us to represent these group elements combinatorially as sort of pairs of binary trees. So this splitting procedure gives us a binary tree and vice versa. And because we do two splittings, two partitions, we get two binary trees with the same number of leaves. And there's a bit of redundancy. So this is actually an equivalence class of pairs, and it behaves very much like a fraction because we can kind of split corresponding subintervals in half and not do anything to the actual picture here. T and V, what you do to get the fraction picture here is just add in a cyclic or respectively any permutation between the leaves, and we draw it like this. So what this amounts to saying is that F is the so-called fraction group of the category of binary forests. So going from the category of binary forests, so just think the collection, the set of all binary forests, to F is much like going from like the integers to the rational numbers, or in general, or more generally, from like an integral domain to its field of fractions. There are small caveats, but we don't need to worry about these so much right now. Just for the discussion, I'm just going to recall for you what the derived subgroup of a group is. It's the subgroup generated by all commutators, which are elements of this form here. And it was shown by Thompson in 1965 when these groups were first defined that the derived subgroup of F as well as T and V are simple. And moreover, T and V give us the very first examples of finitely presented infinite simple groups. So I'm just going to digress slightly into Jones technology, which is going to be part of the motivation for this forest-skein group construction. So Jones technology is this powerful new construction which produces actions, many actions for fraction groups. And this was pioneered by Fields medalist Vaughan Jones within the last sort of 10 years. And kind of what you do is you take a nice enough category. This is one that admits a fraction group like Thompson's group F. You take a complete category, so you can take sort of limits, and you take a functor between these two categories. And this Jones technology machine produces for you a group action of the fraction group on some limit object in your chosen category D. And the whole upshot of this is that the input data is often easier to understand, while the output data gives you some sort of sophisticated action or representation that can tell you lots of things, lots of non-trivial things about this fraction group here. So this was initially kind of used to study Thompson's group F, but it really applies to any sort of fraction group you can come up with. And there's already been many examples, for instance, in representation theory, physics, knot theory, and group theory. So I'm going to motivate a little bit more what we want to get out of this so-called forest-skein group construction. The idea is to take that category of all binary forests that we had that gave us this fraction group picture of Thompson's group, and augment it a little bit, perturb it a little bit, so that we still have the required, still have the conditions that give us a fraction group. These are cancellation and the OR property, but we don't need to think too much about what they are. And we're going to be inspired by Jones' subfactor theory. Basically, what this means is that we're going to try and introduce some relations in our category, relations between sort of these pictures, much like planar algebra. And there's a well-established theory of Patrick Daunois that is going to allow us to check that those first two properties are going to be met for our sort of augmented category. So the idea then is that if we can come up with such a construction, it could produce for us many explicit examples of new groups, and they're going to be compatible with Jones technology by construction. So we've got a lot of angles of attack to study these groups. And most importantly for us, because we're not so far away from Thompson's groups, we have the potential that this class of groups will permit us to construct many new examples of finitely presented simple groups, which is what we want to do. So I'll describe now exactly how we do this. The perturbation we kind of make on the category of binary forest is to add in multiple different carets, so multiple different types of morphisms from 1 to 2. And these we can represent as just coloring vertices, certain vertices. So for instance, you take sort of a fixed color set. I've represented here this by blue and red, and we color all the non-leaf vertices of our binary forests. What this allows us to do is to implement so-called skein relations, which are just sort of pairs of binary trees, pairs of colored binary trees rather, such as this one. And if this quotient is still cancellative and odd, then we are allowed to build a fraction group, which consists of all elements of this form. You just take these sort of pairs of binary trees, but now the difference is that we have some colored vertices, and these are really binary tree classes, colored tree classes. And the group structure here is fraction multiplication. What you do, you take two of these so-called fractions, make sure that the denominator of the first one lines up with the numerator of the second one, and then we cancel and form a new fraction that has numerator of the first one, and denominator of the second one. And this formula is permitted to us by the OR property, and it gives a well-defined product because of cancellation. And the identity is just where you take the same tree on the top and the bottom. You can also build T and V type analogs, and this is just done in the exact same way that we saw how T and V were to F in that initial slide. You just put in either a cyclic permutation of the leaves or an arbitrary permutation. And this gives us analogs of T and V as well. So I'll just talk about some properties that these groups kind of have, without having looked at any examples, what you can show is that Thompson's group F always embeds inside any of these forest-skein groups. So what that means in particular is if you can produce one of these groups, it's going to be non-trivial, it'll be infinite, and it inherits already a lot of properties from F, such as exponential growth and the infinite geometric dimension. In terms of finiteness properties, so some very easy conditions you can place on the category F, such as having only finitely many colors and finitely many relations, gives you a finitely presented forest-skein group. And even there are some sort of mild restrictions that give you that these groups are type F infinity as well. So they're quite finitely presented very often. And for those interested in sort of more analytical properties, there are examples of forest-skein groups that have the Hagroff property. And moreover, even the F-type groups can be non-amenable. But what can we say about simplicity? Well, let's maybe have a look at some examples to kind of get a sense of how these groups behave. And to do so, I'm going to introduce to you this irrational slope Thompson group that Sean Cleary came up with in the early 2000s, late 90s. And what you do, if you remember back to the description of Thompson's group F, where we just cut our unit interval in half into two equal length portions, this is sort of an augmentation of that construction where we allow for now two different types of bifurcation. And this is given to us by the small golden ratio tau, because it satisfies this nice property that tau squared plus tau equals 1. We can actually split in the ratio tau and split in the ratio tau squared. And then we build a group called F sub tau out of these sort of pairs of partitions that you get this way. However, there's some sort of redundancy in that if I split in the ratio tau and then I split the left subinterval also in the ratio tau, represented by these blue lines here, and I do the same for, I split the subinterval, sorry, I split the interval in the ratio tau squared and then the right subinterval then in tau squared again, I actually end up getting the same partition. And so we can realize this if we like as a skein relation and write down an FS category. And this ends up being an OR FS category that is cancellative. And moreover, we have an isomorphism between this abstract forest-skein group and Cleary's rational slope group. And so the kind of thing we want to get out of this is that there are forest-skein groups with good simplicity properties. So this was shown by Barillon and Sinkers and Reeves a few years ago, that Sean Cleary's irrational slope group has simplicity properties that are analogous to Thompson's group F. Cool. Okay. So their proof relies on this sort of action that we have on the unit interval. There are lots of standard techniques one can use there. So we might ask, okay, do all forest-skein groups kind of admit such an action so that we can sort of have a look at trying to prove simplicity in general? And this is somewhat the case. You have that any forest-skein group acts in an order-preserving way on a totally ordered set that we call Q sub F associated to F. And this was shown by Brothier in last year. And I'll just give you an example of how this sort of works. So if you consider that example in the previous slide, the irrational slope skein relation here, what you do is you replace what are called the dyadic rationals, which Thompson's group F acts on. So these are just all the points, just the sort of midpoints of our sort of splitting, all those dyadic rationals in the interval. You replace this with a set Q, and this consists of pointed tree classes. So what you do is you take all the trees in your category and you pick a leaf, and then you say that, okay, I'm going to consider these equal up to. What you can do is you can grow the leaf up to the left is the rule. And the pointed tree class also has knowledge of the skein relation. So this tree here is also equal to this tree here. And then we replace the action of F on the dyadic rationals by 1 on this set Q. And this is given very similarly to the group product. Basically, what you do is you just make sure that this tree is the same as that of the denominator. And we can do this because we take in classes where we can grow. So we make sure to grow this tree so that it lines up with the denominator, and then we just cancel. And the leaf number that we pick stays the same. Okay, so this is kind of the replacement of the action of the on the interval. Okay, cool. So does this mean that we're going to get all sort of simple groups now? Well, we have to look at another example. We're going to consider this FS category here, where I'm taking two colors, just one relation as before. However, this might look very similar to the one that we studied before, but just notice that this red tree, I've moved this caret over to the left. And so now my skein relation is built of two colored trees, but the underlying tree is the same. And it's because of this that we get a surjection onto F. So G ends up being quite far from simple, as sort of an extension of F. More precisely, we can show that the forest-skein group in this case decomposes as this permutational wreath product here, where F acts on these finitely supported functions by just shifting. And we can show that the canonical action that we mentioned in the last slide is just given by this formula here. And the thing to note is that Q2 doesn't know anything about this left factor here. And so we get a kernel given by the whole left factor. So the point is that the canonical action of a forest-skein group is not always faithful. And that's one of the key things to apply these sort of simplicity techniques. We want to be sort of a subgroup of some homeomorphism group, which we're not going to get here. So let's just think about some properties of the canonical action that we've sort of witnessed. So one thing that you have is that Q has an inf that we'll call O and a sup omega. We'll want to refer to this later. So that's just like 0 and 1 of the interval. Q ends up being dense in a Cantor space, so that's kind of good in terms of some techniques we might want to apply to try and show simplicity. However, we've seen that the action is not always faithful, so we can't always realize G as a subgroup of the homeomorphism group of Cantor space. And moreover, you can actually show that this kernel is going to be isomorphic to its square. So when it's non-trivial, it's actually quite large. It's going to be infinite and not simple, for instance. Okay, so we just have to, we now kind of want to figure out when do we admit a canonical, when do we admit a faithful canonical action, so that we might be able to start applying some of the techniques that we have available to us for groups acting faithfully on a Cantor space. So the way we're going to do this, the way we're going to try and find simple forest-skein groups, we're going to look for non-abelian quotients, because we're interested in more so getting that the derived subgroups of these groups are simple. That's what we can hope for. Okay, so let's think about our example that we had that gave us this extension of F as one of our non-simple ones. Okay, so it was given by this skein relation here, and we saw in one of the previous slides that we could write it as the semi-direct product of F with some large non-trivial group. Okay, this is sort of normal inside G, and if I quotient out by the kernel, I end up getting F. This is what we want to observe. And now F itself can be represented as a forest-skein group just by having one color and no relations. And we know F has good simplicity properties. So we might just ask, if we get rid of the kernel, if we quotient by the kernel in general, do we get something with kind of good simplicity properties? And here's sort of a partial answer to this. Well, if you take a forest-skein group, then there's always going to be a sort of another forest-skein category that gives you the quotient of that initial group by the kernel of its canonical action. And moreover, this group that you get, it acts faithfully on with its canonical action. So then we wonder, is it enough to have a faithful action to admit these good simplicity properties. So unfortunately, there are some other ways you can get non-abelian quotients as to kind of restrict from having directly analogous simplicity properties to F. To see this, I'll just kind of quickly mention this notion of a group of germs with respect to an action. So if you have a group action on a space by homeomorphisms, then the germ group is you take all those homeomorphisms that fix a particular point. So we have an input point, and you take that mod out by all those homeomorphisms that act trivially on a neighborhood of X. And so because G acts in an order-preserving way on its totally ordered space, and we have an infinite soup, we fix those points, O and omega. And so that means we can actually get quotients in the form of germs. And one example to consider where we get sort of a non-abelian germ group at one of these extremal points is this one here, where we take this one-skein relation. And we actually get a quotient, which is given by this germ group at the left extremity O, associated to the canonical action. And it can be shown that this group has a presentation given here. And this is a non-abelian group. And just a thing to notice is that this comes from just reading off the left side of your skein relation. We've got 3 A's because we've got 3 blue colored vertices here, and we've got 2 B's because we've got 2 red colored vertices here. So it is sort of a relatively easy thing to see whether or not you admit a non-abelian quotient in this way. And so we get that the derived subgroup of G is not simple because of this quotient here. What about T and V? So you can actually also admit quotients of the T and the V types. And this was also shown by Barillo and Sinkus and Reeves in their study of the irrational slope groups. So their T and V variants quotient onto Z mod 2, which is just given by taking counting mod 2 the number of red vertices in your fractions. However, the derived subgroups are simple in this case. There's no other sort of obstructions. And in general, we do have that's basically it. If you take some forest-skein data, so a category, a group, and its canonical action, just very quickly, I'm going to introduce this idea, this notion of this subgroup K, which is just the subgroup of all elements that act trivially near O and omega. So for people with familiarity with Thompson's group F, this group is just the derived subgroup of F in the classical case, but generally the derived subgroup of a forest-skein group, it doesn't have to act trivial near the extremities. Okay, so given any forest-skein group, we get that if the kernel of your canonical action is trivial and you have your germ groups being abelian, well, that's it. Then the derived subgroup is simple. If your canonical action is faithful, then you already get that the derived subgroup of GT is simple. And similarly for the V type as well. So some interesting kind of strange stuff is happening with the F case, but the T and the V case, you just need to act faithfully on your canonical space. And moreover, a converse holds. If you have a simple group sort of nested in between the derived subgroup of this K group here and GV, then you already know that you act faithfully on this space. Okay, so this is all well and good, but if we don't have any explicit examples to show what is this good for, well, so given our sort of motivation with this clearly irrational slope group and the forest-skein formalism, it sort of is suggestive that it fits into this larger family of forest-skein groups, which are determined by this skein relation, where you just keep growing up to the left. You take these 2 trees equal. So I have, for this index n, I have n colored vertices here instead. And these behave somewhat similarly to the irrational slope group, but also quite differently. But you are able to show that the canonical action you get is faithful. This is actually relatively non-obvious to show. It's quite difficult in general to show this. This is really the crux. And we have abelian germs. This is not too hard to show. So by the previous results, we get that the derived subgroups are simple. And moreover, we get that the T and the V versions are finitely presented and simple. And so just to summarize very quickly, we're interested in finitely presented simple groups because we don't know very much about them. The forest-skein formalism admits many groups with good simplicity properties because we just quotient out by the kernel, we get some simple T and V groups. However, it is generally quite difficult to find what are the actual explicit presentations that give you these groups. And also, surprisingly, not all forest-skein groups are simple as well. And so we ask, the main question I'm working on at the moment is, when does a skein presentation give you a faithful canonical action so as to admit many explicit examples of finitely presented simple groups? So thank you for listening.
Thank you, Ryan, for the talk. Does anybody have any questions? I guess my question is, do you have any sort of ideas or just special examples of relations that have been giving you a simple groups, but you don't know if they live in some sort of bigger family of relations?
Yeah, so it's very easy to find examples that have a non-trivial kernel. So we have a large class of examples that admit non-trivial kernels. However, it's kind of hard to see. Yeah, and so we sort of conjecture that, like, if you're not that, then you will have non-trivial kernel, but it's surprisingly challenging to sort of show.
Yeah.
I do have a sort of extra slide here. Playing this game of sort of asking when you have a non-trivial kernel, maybe it's got something to do with having the same shape. This is kind of the example that we saw. We took the same shape tree and we surject onto F just because we can forget the color. Okay, so then maybe you go, okay, maybe it's having a non-trivial kernel has something to do with having the same shape. So what about this one? These two trees are different shape. Do you think this admits a forest-skein quotient? So this one also does, because there's some sort of hidden structure here. I can, in a sense, these trees do look the same if I kind of take my sort of unit cell to be kind of different. So this we call sort of quasi-shape preserving. And sort of we would think that if you don't admit an obvious forest-skein quotient, then you should be faithful. But yeah, other than the family of Cleary groups, it's been hard to show. Yeah.
Cool. Yeah. Well, it's very interesting that you can produce so many different simple groups suddenly. So yeah. Does anybody have any questions? And if not, we can thank Ryan again.